the reason we don't really understand inverse trig functions is because we just started using it and punching into our calculators before we started a bit further back and gave some context. Okay? So on your heading, if you wrote it the right way, where we need to begin is not with inverse trig functions, but with functions and relations. Okay? Which is something you might have looked at the end of year 9, and you might have no memory of because often it's done just before the exam or even after the yearly exam. So it goes out of your brain pretty fast. Okay? So make this subheading. And let's give this a go.
Wait, is this the heading, original heading is function?
Yeah, so this is the real heading you're making, okay? So functions and relations.
Put it underlined.
You said that, however.
You lied to us.
Yeah, don't worry, I wrote introduction to truth.
The heading is a lie. Okay.
The introduction to inverse trig functions.
Now, let's just remember what are functions and relations. We'll start with relations first. In reality, right? Oh, sorry, question?
Oh, no.
You were going to give it, okay. We come up with related numbers all the time, okay? Pairs of related numbers often, okay? So for instance, something's mass tends to be related to its size, yes? Okay? The temperature outside tends to be related to time, okay? And I could go on and on and on. Whenever you've got two quantities or values or variables that are related to each other, we call that a relation. Right? It's a relationship, and if you can express it mathematically, you could write it as an equation. Okay? So for instance, that's a relation. Okay? That's a relation. You see there's a connection between the two numbers. Okay? They're not independent, flying off and doing whatever they like. When one does something, it affects the other. Okay? Now, functions, I should have drawn this a bit different way. Let's make this a bit bigger. Functions are a subset of relations, okay? They are the special kinds of relations where, now, does anyone know what the difference is? Yeah.
You cannot have two y, wait.
Okay, hold on, pause, stop. Now, okay, fine, I'll get to that in a second, but let's just come back, okay? What does it have to do with when you've got two numbers? What makes a function when you've got two, like say, size and mass, or time and temperature? What is it? What characteristic about those two makes it a function more specifically, not just a relation? Okay. Now, the answer is right that each. Let me get this right. For a function, okay. Each output. Yeah. Let me make sure I get the order right. Each output. No, wrong way around. Each input has only one output. Okay? So you should get that down. That's a really important idea, okay? Because it's going to come back and bite us when we start thinking about trig tomorrow, Monday. Each input has only one output. Now in Cartesian terms, which is what Richard, you jumped to, okay? That means each x, because we call our inputs x usually, right? Each x has only one y value to go with it.
What if it's got a restriction?
Okay, I'll get to that in a second. So let's just think in general terms, okay? Now, if you wanted to test how that would work out, okay? Let's have a look at these, for instance. Okay, I probably should have written that like so. So what does that look like as a graph of that function? It goes across like that. You got a point like 2, 1. Okay. Geometrically, what you can do is they call it the vertical line test, right? Because if you take a vertical line, that means for each x value, you'll check how many y values there are, okay? And the number of times your vertical line intersects, for instance, once, okay? For all values, since there's only one output, that's what classifies this as a function, okay? Of course, when you move to other kinds of relations, if you slap the vertical line in, right? Well, for all of the values for which this relation exists, except for here and here, that vertical line is going to hit twice, right? So you've got two outputs for each input, which is why this is no longer a function. Okay? All right, now, if that's what functions and relations are, how do they relate to inverses? Okay, so make a little subheading. How would you define an inverse in English, in plain language, without talking about x's and y's? You talk about inputs and outputs. What is an inverse?
You switch them around.
Switch what around?
The inputs with the outputs.
What does that mean? Negative reciprocal? Maybe. Depends.
Just reciprocal.
Now, okay, we're trying to get at what is it that turns, what does swapping inputs and outputs mean? Okay, so for instance, if I took this here, okay, and swapped them, so I get this. Okay, well, what's that about? What's the purpose of that? And the answer is the reason why this is important and why we call it an inverse is because it it specifically reverses the process that this does. Okay, so this takes an input, right? Should we go with this one? And halves it. Okay, so there's a process, and you'll only have one output for every input that you put in. Okay, but what does this do? It takes your input and it doubles it, which is exactly the opposite. It's undoing what this does, if you like. Okay, so again, in Cartesian terms, you swap your x and y. Okay, now this is a function, right? And if we graph this, right, what you get is also still a function, right? Because I can do my vertical line test. So this is an inverse function. No problems, okay? But you can imagine, right, and it's not that hard to think of examples, that you can start with some functions, and when you do the inverse, when you swap your x and y's, you're not going to get a function back. Okay, can someone give me an example? Okay, so let's take this guy.
Absolute value.
Okay, y equals x squared. Is it a function?
Yes.
It is, right? Because when you graph it, you put your vertical line across, and it always intersects once. There's only ever one output, okay? But what's the inverse of this? What's the inverse? Well, you just swap around your inputs and outputs, right? Yeah. So let's do that. Okay, now I've swapped them. This is the proper inverse of this, okay? This is the function. Now, what does it look like? Yeah, good. It's going in the... Oh, I missed totally. Oh, well. Make yourself a new axis when the old one doesn't suit your purposes. Okay, so there is x equals y squared. Okay, and it is clearly not a function. Okay, so it is the inverse, but it's a relation, right? Okay. Now, we can do things to this so that when we take the inverse, you'll just get a function. And what would you do? And the answer is, yeah, you'd place some kind of restriction, okay? Now, let's think about this. I actually have some choice, right? Where should I place the restriction? I can put it in one of two places.
Can you actually do it anywhere as long as it doesn't... Like, you make it
If all I want to do, I'll get some new colors here. If all I want to do is make an inverse function, right? No green.
X is greater than pi divided by...
Okay, so if all I want to do is make an inverse function, any inverse function, then either of these choices would be fine. I can take this domain over here, x is less than or equal to 0, or I can take the other side. Now, quick question, by the way. Why is it that 0, the origin, why is it that this is the point where I go one or the other? Why can't I go, like, say here or over there? Or why is it that point? What's special about it?
Because that's
More specifically, you're on the right track there. It's the turning point, right? And a turning point is what breaks the inverse relation over here. When it turns, that's when you start to fail the vertical line test. Okay, so just file that away, right? The reason why I'm choosing the domain here, why this is the switching point, is that that's where the turning point is. Okay. Now, suppose I chose the left-hand side. Okay, actually, I'll do it in green. What would be the inverse function if I only took the left-hand side and took the inverse of that? What would be the inverse function of that restriction on the domain? Okay, so if I'm going to do it geometrically, okay? So you remember, one of the ways that you can go from a function to its inverse is you flip it, you reflect it, but where do you reflect it?
You reflect it, you flip the whole thing like that. Like you bring that, on the two stilty bits, you go... Wait, can I...
Right, okay, so two different answers, they're both fine.
Is that y equals x?
You can take that line, right, that there 45 degrees, that's y equals x, and if you turn your head, that's where I'm going to flip it, okay? I'm going to reflect it across that line. So what are you going to get? You're going to get this line, right? That looks symmetrical, doesn't it, once you turn your head properly? Yeah? It's pretty good. All right. Now, what is the equation of that inverse function? Okay, well, it's underneath the axis, right, for all values of x. So I know there's going to be a minus at the front, okay? And the rest of its characteristics I get from this, right? So I would take the square root because I only want the bottom part. Okay. Now that would work just fine, okay? But why would we, avoid that kind of inverse function? Why wouldn't we choose that? Like, what are some suggestions for, why it's maybe not the best choice? Negatives are lame. That's true.
Green and
We don't
seasick.
like. I could swap the colors. James, x has to be bigger than 0.
Yeah,
Well,
but
X
in
does
the
have to be
other
bigger
y
than
has
0,
be
but if I took either one, x would still be greater than 0.
because in the original
Because it'll
one,
always
y
be,
is basically-
yeah, exactly. So the range and domain are swapped. Now the reason why I'd probably suggest why it's like that's a weird way to go is that square roots and squares, they often come up with measurement, right? Like with distances, okay? So it would be weird if you thought, now what's the way to reverse this? Let's take negative values, okay? That's unusual. That doesn't fit the use cases for, why we take the inverse function, okay? So therefore, it kind of makes more sense to just take this side, right? And that's why we land with, that's why the calculator will give you the positive values, because we've told it to, right? Not because there's some innate thing, but this makes more sense to us, okay? And you can see, if I flipped it, that's where the shape comes from. Again, you can turn your head and you can see the symmetry, okay? So this idea of taking a function and restricting its domain in such a way that you get an inverse function out, okay, is really critical, okay? In fact, it's going to be the building block for when we move to inverse trig functions, especially the fact that you can choose lots of different ways to do it, okay?